Hello everyone, I'm Paul Agbaje, a PhD student from the University of Texas Arlington. I'll be presenting our work on a framework for consistent and repeatable controller area network IDS evaluation. CAN provides a simple and efficient communication standard for in-vehicle ECUs. Although CAN is fault tolerant, it implements no security mechanism. It is crucial to protect critical systems on the bus from cyber attackers. And one way to do this is by designing intrusion detection systems to flag anomalies in the network. However, existing IDSs pose various challenges that make it very difficult to compare their performances. IDSs use different data sets for their algorithms and also make assumptions that are particular to individual algorithms. These assumptions are very significant in determining the performance of these algorithms during the evaluation phase. Also, during evaluation, these algorithms use different data sets and also different metrics for their performance evaluation. For example, some may use false positive rate, others may decide to use detection rate or precision or accuracy. These differences and inconsistencies make it difficult to compare these algorithms. To address these challenges, we designed a flexible framework that allows for the fair comparison of different IDS algorithms. And also the framework is extensible such that new data sets and algorithms can be added for comparison. The framework has a preprocessing stage where empty columns in the data sets are padded and the data is encoded such that the algorithms used by the framework can make use of the data. To make the framework robust, we consider three classes of algorithms: the timing-based algorithms, the statistical and machine learning-based algorithms. The timing and statistical-based algorithms make use of the attack-free data set to estimate a threshold that is used for anomaly detection. The machine learning algorithm makes use of part of the attack data set for its training. After testing is done, we evaluated the performance of these algorithms using 5 evaluation metrics, namely the recall, the precision, F1 score, accuracy, and false positive rates. The timing-based algorithms use inter-arrival time of messages for anomaly detection. For timing-based algorithms, we considered time interval-based algorithms and a frequency-based algorithm. The time interval-based algorithms use inter-arrival time of signals for anomaly detection in CAN signals, while the frequency considers the frequency of unique IDs in a time window. The statistical-based algorithms detect anomalies based on statistical models built from the attack-free data sets. For this class of algorithms, we consider the cumulative sum, which considers the cumulative change point of specific IDs in a time window, the entropy base, which checks for the probability of an ID appearing in a specified time window, the graph base, which converts CAN messages into a graph structure, ID sequences that monitors the sequences of unique IDs, and army distance-based algorithm that calculates the army distance between different CAN payloads. For the machine learning-based algorithm, which considers or identifies patterns in CAN messages, we considered an artificial neural network that has 1 input layer, 2 hidden layers, and 1 output layer. To evaluate the performance of the algorithms, we used recall, precision, F1 score, the accuracy, and FPR. The recall gives us an idea of the proportion of correct attack predictions when we consider messages that are labeled as attack in the data set. The precision tells us the proportion of identified attacks that were actually correct. F1 score gives us a much more robust view when considering both recall and precision for all the algorithms. The accuracy tells us the proportion of right predictions in the total observation by each of these algorithms, and the FPR gives us an idea of the false alarm rates from each of these algorithms. For our framework, we use dataset provided by the HCRL lab, which contains denial of service attacks, fuzzy attacks, RPM, and guest spoofing attacks. The DOS attacks contains attack injection, which comprises of injecting high priority messages in the CAN bus to deny services to legitimate nodes. Fuzzy attacks dataset contains randomly forged messages. The RPM and guest spoofing attack contains fabricated messages. And we can see from the result from the time interval and frequency, we were able to measure the performance of these algorithms using our 5 metrics of recall, precision, F1 score, accuracy, and FPR. What we notice is that timing interval algorithm, that is the time interval and frequency algorithms considered, were able to detect fuzzy attacks well, and we're able to flag intrusion, or we are able to flag aberration from the expected pattern of a CAN ID. And they perform really well on fuzzy attacks as seen from the results here. For army distance was computationally inexpensive and was able to flag denial of service attacks very well, with very low false positive rates and high accuracy. And this is because these kind of attacks do not rely on different attributes of ECUs. However, graph-based and machine learning-based approaches are able to discover correlations among different features of CAN messages, and so are able to flag intrusions much more accurately than other algorithms, with very low false positive rates and high accuracy when compared with the performance of all other algorithms. Due to this, we suggest that future intrusion detection system design should consider machine learning based models and graph based models, which are more suited for CAN bus datasets. And also, the framework we provided can be used as an evaluation platform or as a benchmarking tool to test the performance of different IDS algorithms to facilitate fair and reproducible experiments. Thank you. Questions and comments are welcome. Thank you.